Hi guys, we're going to back up a little bit here and get Rutherford's model of the atom back in our mind. Remember he had a nucleus here, and inside the nucleus were protons and neutrons. And then orbiting that nucleus in concentric circles were electrons. And that was the model that he came up with, where the atom was mostly empty space but had a hard, dense, positively charged nucleus. But he knew that there were some problems with it. For instance, his problems were, why don't the protons fly apart? You've got positively charged protons right next to each other. They should repel each other. Likewise, why don't the negative electrons fall in towards the nucleus? They're negative, and those should be attracted to the positive protons. They should just kind of orbit in like this and fall in towards the nucleus, but they don't. Those were problems for Rutherford, as well as he saw that the electrons could be on one level, or the next level, or the next, but he noticed that the electrons could never be in the in-between spaces. He thought that was peculiar, and he couldn't explain why. So he put those three problems out there in hopes that someone else would add on to his model or revise it. And the guy that did that was Niels Bohr. Bohr's idea was pretty wild. He said, instead of thinking of electrons like tiny little particles, maybe we should think of them as waves. Because waves have these quantized properties. Waves can be in certain places and not others. We saw in the spring demo that when two waves collide, they may collide in phase, like this. In which case, their resulting wave will just be a bigger wave. The resulting wave has twice the amplitude, goes up twice as high and down twice as low. This is called constructive interference. If, on the other hand, waves collide and they are out of phase with one another, where one wave is up when the other one's down, then the resulting wave is the average of those two, which will just be a straight line. In other words, they cancel each other out. This is called destructive interference. With that knowledge, Bohr can now explain why electrons can be in certain places and not others. So you just have to imagine, if this is the nucleus and the electrons are orbiting around it, that they're actually orbiting in tiny little wave patterns, and maybe they come back on itself and it's in phase, in which case you get a nice standing wave there. Constructive interference. Scoot out a little ways from the nucleus, and the wave may come back in on itself and be out of phase. In which case we're not going to get a nice standing wave here. We're going to get destructive interference. That purple wave is going to cancel itself out. So there's not really going to be a wave there. If we go out a little bit further, maybe now it's back in phase with itself, so we'll get a nice standing wave there. Go out further, and maybe this time it's out of phase, so we would get no wave there. And so what you get is an alternating pattern of standing wave, no standing wave, no standing wave. Well, what are the waves? The waves are the electrons. So basically, Bohr has explained in his model how you could have an area where the wave exists, and then an area where the wave is forbidden, and then an area where the wave exists. So you could have electrons on any given energy level, but never existing in the space. Since electrons act like a wave, it can only orbit the nucleus at specific distances. Remember, an electron's energy is related to how far it is from the positive nucleus. An electron on the bottom energy level has a small amount of energy. If it jumps out to the next energy level, it has more energy. If it jumps out to the next energy level, it has even more energy. Since the electron can only be at certain distances from the nucleus, then it can also only have certain energies. This is why when we looked at the light spectroscopy demo, we only saw specific colors, specific wavelengths. For hydrogen, we saw a sharp red color because the electron could jump out to level 2 and fall back down, or jump out to level 3 and fall all the way back down, or jump out to level 3 and fall back down to level 2. Each of those jumps is giving off a different energy, which is seen as a different wavelength photon, and your eye perceives that as a different color. So each time an electron falls down, a photon of energy is given off and strikes you in the eye. And then you see that color. There's a name for properties that can only be in certain places and not others. Properties with specific allowed values and forbidden values are called quantized properties. Therefore, we say that electrons have quantized positions, because they can only be in certain places, and quantized energies. In our next video, we will take a closer look at where the electrons can actually be, and how we can describe where all the electrons are in an atom.